Hello everyone, welcome back to Nated Engineering once again. It's the second video of the refrigeration power machines N6. I want us now to look at the TS diagram of water, how steam is generated. The TS diagram is temperature and this is entropy. If you're wondering what entropy is the measure of disorder. Let's take this example. We're having ice. We know that, okay, let me write it here. We're having ice. We know that in an ice we have particles, and the way we have been taught is that the particles are closely packed together in an ice, just like this. So what happens here is that we add heat energy and this ice is converted into what? Into water. And then now, according to what we have been taught is that the particles are no longer closely packed together as they were on the ice. Then we keep on adding heat energy into this water. What is it turned to? It is turned to vapor. And then what we've been taught is that the particles are very scattered in the vapor state. This is steam. So when you go in that direction, you can see that the order is decreasing. Here they were closely packed in order. Here they started to scatter around. Here they are very scattered. So going in that direction, you can tell that the order is decreasing, meaning entropy is decreasing. It's increasing rather, because we know that entropy is the measure of disorder. When it goes to that direction, the disorder is increasing. But when you go to that other direction, now the order is increasing when you get to vapor, water and ice, meaning if you were to go in that direction, our entropy will be negative. Here in the TS diagram, we are looking at how is steam produced. We know that the boiling point of water, for any liquid, in fact, not just water, it's dependent to the pressure. So whenever you are asked what is the boiling point of water, the question that you should ask is what is the pressure? Because the assumption that the boiling point of water is 100 degrees Celsius, it's wrong. Especially when they are going to give you, when they are going to ask for the boiling point and then they give you a different pressure, which is not atmospheric pressure. Water will only boil at 100 degrees Celsius only if we are dealing with atmospheric pressure. If the pressure that is applied on that water, on the surface of that water, it's not 100, it's not atmospheric pressure, the water will not boil at 100 degrees Celsius. So if the pressure increase, the boiling point will also increase. But if the pressure decrease, the boiling point will also decrease. So whenever you ask for the boiling point, you should ask for the pressure and then go to the steam table and get the correct saturation temperature or the correct boiling point. And then we come back to our graph. From here, we are having water. What happens when we add heat energy to water? Obviously, the temperature will increase. That is represented by this line from here. Say A, B. It's I was supposed to say what? Okay, let's name it Z. That is represented by the line from Z to A. So from Z to A, we are increasing the heat energy, and as a result, the temperature of the water is increasing from Z to A up until it gets to point number A. Point number A is where now it has reached its saturation temperature. Let's assume we are using atmospheric pressure. It's saturation temperature, which is 100 degrees. Now, when the water gets to 100 degrees, it stops increasing in temperature. So from here to here, this is where the water reaches its boiling point. And the heat energy that is added from this point to this point is called the sensible heat. And we are going to have the enthalpy of water here being HF. F is the symbol that we use for water in this case. HF represents the enthalpy of water. And then we come back Now, we said the water is no longer increasing in temperature. But what happens, because still heat energy is being produced to the water. Now the heat energy that is produced will no longer be used to raise the temperature because we have already reached our boiling point. Remember, water can never exist in a temperature which is higher than its boiling point. Now from this point, the heat energy that is used to convert the heat energy that is produced rather is used to convert the water from water to steam. So from here, the water is being converted from water to steam, which is from here to here. And the heat energy that is added in that case is called the latent heat from this point to this point. And the symbol of up until we get to this point where now all of the water has been converted to steam and it is dry saturated, which will be Hg. The heat energy of that steam will be Hg. The latent heat is HFG. So from A to B, the heat energy that is produced is used to convert the water to steam, meaning between these 2 points we are having wet steam, because steam and water coexist between these 2 points. So we are having wet steam. Point B is where now all the water has been converted to steam, and then now we're having steam that is dry saturated. It's dry saturated because it still has the temperature which is our boiling temperature or saturation temperature. And then from B, the heat energy that is added now will no longer be used to convert the water because there is no water anymore. It's now used to raise the temperature of the steam, and then that's what we call superheated steam, which will be superheated steam, and it is H soup. The heat energy that is added from that point, it's called sensible heat. Again, sensible heat, it's associated with temperature increase. When heat is added and the temperature is increasing, we call that sensible heat. When now heat is added but there is no temperature increase, which means it's phase change, that one we call a latent heat. We said the boiling point of water will depend on the pressure by which that water is subjected to. And then now, let's say we are to raise the pressure. What will happen to the boiling point is that it will increase, and we are going to have something like this, a diagram like this. And if we keep on increasing the pressure, we're going to have lines like this up until we get to a point which we call, let's write it here, we call it the critical point of water. And then if you were to join these lines, you are going to end up with a diagram like this. We know this part is the subcooled, which is temperature lower than the saturation temperature. In here, that is where we have wet steam. Out here, that is where we have superheated steam. This line represents the saturation temperature. This line represents dry saturated. So we will end up with two diagrams like this. This is the TS diagram. This is the pH diagram. Here it's subcooled, wet steam, superheated. This line represents the boiling point or saturation temperature, and this line represents the dry saturated. Same applies to this diagram. This is the TS diagram, which is temperature entropy. This is the pH, which is pressure enthalpy. So these two diagrams are where we are going to represent the information that we are given from a question. I want us now to do a question to see how do we use these tables to represent the information that we are given in a question. The example that we are doing, I've taken from my textbook, and it reads as follows. A simple heat pump circulates Freon 12 and is required for space heating. The heat pump cycle consists of an evaporator, a compressor, a condenser, and a throttle regulator. A throttle regulator being the expansion valve. The pressure limits in the cycle are 0.491 megapascal and 1.219 megapascal. The heat transfer required from the condenser unit is 100 megajoules per hour. The Freon 12 refrigerant is assumed to be dry saturated at the beginning of compression and to have a temperature of 55 degrees Celsius after compression. At the end of the condensation process, the refrigerant is liquid but not undercooled. Assume the specific heat capacity of the superheated vaporized constant. And then we are given a table. They say it's the relative properties of Freon 12. We're given the pressure, saturation temperature, specific enthalpy, and specific entropy. So now we are given information we want to represent in these two tables. We have the TS diagram and the pH diagram. According to the table that they gave us, I have already taken the temperature, the saturation temperature in this pressure, and this the saturation temperature in that pressure. We're given two pressures and we're given two saturation temperature. And then let's start. They say the Freon 12 refrigerant is assumed to be dry saturated at the beginning of compression. At the beginning of compression, it's assumed to be what? Dry saturated. Beginning of compression, it's low pressure because it's before the compression. We know the compressor is the one that will raise the pressure. So we're dealing with this pressure. They say it's what? Dry saturated. Which line represents the dry saturated? This is the line that represents the dry saturated. So we're using this pressure and we are within this line. Even in this diagram, that's where we're going to put our point. And we continue. They say, and to have a temperature of 55 degrees Celsius after compression. Now, they say after compression, the temperature that you are going to have is what? They say after compression, the temperature that you are going to have is 55 degrees Celsius. According to the table, we know that the saturation temperature at this pressure, since it's after compression, meaning the temperature is already being raised to this value. And then they say after compression, the temperature is what? Is 55 degrees. 55, let me write it. 55 degrees Celsius. We know that this is the saturation temperature. What does that tell us? It tells us that this will be superheated steam because now it is existing at a temperature which is above its saturation temperature. That will make it superheated steam. Remember the condition that I gave you on our last video or previous video where I said it's always the case where S1 is equals to S2, meaning now from here we're getting from 1 to 2. S1 is equals to S2. We're going to go up straight up until we reach the saturation temperature line. And then from here, what happens during compression? The pressure is increasing, also the enthalpy it's increasing up until we reach this pressure. And then they say at the end of condensation process, the refrigerant is liquid but not undercooled. Now we know that the condenser, that is where we are discharging the heat energy. So we are here at this point. This is point number 1 and this is point number 2. Number 1 and 2. We are here at this point. The heat energy is being lost. First, it will get from the superheated temperature to the saturation temperature, and then we start the phase change up until we get to this line. Even here, we're going to draw it up until this line. We are told that the refrigerant after the condensation, it is what? Liquid but not undercooled. So it is within this line because it is not undercooled. If we were told that it is undercooled, it will have been within this region. But since we are told that it's not undercooled, we are going to put it in this line. And then what will happen now is that we are going through the expansion valve. The expansion valve, what will it do? It will decrease the pressure from that pressure to this pressure. There is no heat added or heat extracted. We're just increasing the pressure. We're just decreasing the pressure. And in this part, we are still on number 3. So we know the saturation temperature will decrease since the pressure is also decreased. Then we are going to have something like this. Notice that the entropy, it's increasing from this point to this point. Why? It is because there is expansion. Remember, entropy, it's the measure of disorder. When the refrigerant is expanding, what happens to the particles within it? And then from here to here, we just join. From here to here, we just join. Here, from this is 4 to 1, that is during the evaporator. Heat is absorbed, meaning the entropy will increase and the enthalpy will also increase since we are adding heat energy to the refrigerant. And that's how we represent information on these two graphs. We have the TS diagram and the pH diagram. And then that's all I had for this video. I will see you on the next video.